Okay, the next set of topics that we're going to discuss is reactions of benzene rings, and we're going to focus on side chain reactions or the reactions that occur outside of the benzene ring. So the first reaction that we're going to go ahead and talk about is how can you break up the aromaticity of a benzene ring. Now we said last time in the last lecture video that aromatic means super stable. So is there a way to actually remove the aromaticity of a ring and just make it into double bonds? And the answer is yes, and this is called Birch reduction. So in Birch reduction, what we do is we actually use sodium metal in liquid ammonia. And if you remember, we used liquid ammonia and sodium back in the reduction of a triple bond. We used Na in NH3, sodium and liquid ammonia, to form the cis alkene, or sorry, the transalkene actually is what we made. The cis alkene was with the Lindlar catalyst, so we made the transalkene. And so remember also, or I'll review here, the idea that sodium metal has one unpaired electron. And so what happens when you put sodium in liquid ammonia is that it loses that unpaired electron, so that basically you make a solvated electron and a sodium cation. So that's what the mechanism of this is going to be. Now I'm going to show you the mechanism to show why specifically you get hydrogens added to the 1 and 4 positions in the ring and form the double bonds that are then isolated. So you're going to add 2 hydrogens opposite positions on the ring, the 1 and then the 4 position. So the mechanism of this reaction involves, first of all, the sodium with its unpaired electron basically releasing it to form what is called a solvated electron in the liquid ammonia. And then that electron can go ahead and add to one of the carbons, and all of these should be half arrows. Unfortunately, my drawing program didn't draw half arrows, didn't have the option, so these should all be half arrows. The fishhook arrows. And so in this case, we had an electron here, and then if we do that, then we take this pair of electrons and what we're going to do is this. We're going to split this carbon-carbon double bond, and we're going to take one of the electrons and pair it up with this solvated electron, and then give the other unpaired electron over here, which then will split this double bond and give one electron here to form a double bond, and then the double bond's unpaired electron will go here. So in the end, we're going to make what is called a radical anion. So this carbon down here where the solvated electron went has a pair of electrons, so it's a -1 charge. Then the unpaired electron ends up here. Now remember that these electrons are basically big clouds of negative charge, so they're going to be most stable when they're opposite each other on the ring, which means they're in the relative 1,4 positions. Then this is now a C-, it's a carbanion. The carbanion, we usually then add some alcohol to this or have some alcohol present. It will deprotonate the alcohol and we'll add our first hydrogen. And then we'll have our radical, and then what will happen with the radical is the second solvated electron will add, so that now we get a carbanion. That carbanion will then deprotonate another alcohol, and so in the end we add 2 H's, but the reason they added in the 1,4 position is because that's where the initial radical anion is most stable. So in Birch reduction, we then end up destroying the aromaticity of the benzene ring, and forming, in essence, a 1, 2, 3, 4, a 1, 4 diene is what we end up making. Now, if there's an alkyl group on the ring, you're going to form the double bond so that the alkyl group makes that double bond more substituted. So, in essence, what we're doing is we're making the more stable alkene. So, that is Birch reduction, and it is a very harsh reducing reagent because I am basically using a naked electron or a solvated electron to do that reduction. So it's a fairly old school method of breaking up the aromaticity of the benzene ring. And then once I do that, I have double bonds that I could go ahead and react. Now, looking at the side chains, looking at alkyl groups that are attached to the benzene ring, let's talk about what kinds of reactions we can do there. And this carbon that's attached to the benzene ring is called the benzylic carbon. And basically it's benzylic because it's analogous to the allylic carbon, where the carbon is attached to a double bond. In this case, it's attached to the benzene ring. So it's benzylic, and that's a special position. And the reason it's a special position is because if I make an anion, there are resonance structures that I can draw for that. I could take this pair of electrons and move it here to form a double bond, but then give this pair of electrons to this carbon. So I could end up with a resonance structure of the double bond there with the negative charge there. And then could take and form the double bond here, and then take that pair of electrons and give it to that carbon. So then I would end up with the negative charge there, the double bonds here, and then double bond there. And then take that pair of electrons, move it here, and give that pair of electrons to the carbon to form my third resonance structure that would look like this. So with three resonance structures, that makes the carbanion here fairly stable. Now I do have to point out the fact that these three resonance structures all do not have the aromatic ring, the benzene ring being aromatic. So they do contribute to the overall stability, but none of these anions will actually react. The reaction will only occur at the benzylic position. The same thing's true here. You could take this carbocation and you could write its resonance structures by moving the pairs of electrons around that ring. And then you can also take this radical and do the same thing by splitting up the electrons and stabilize it by taking the unpaired electron and delocalizing it into the ring. So the benzylic position is a very stable and special position for the reactions of alkyl benzenes. Now, one reaction that we can do with an alkyl benzene, and it doesn't matter what the alkyl group is. It could be methyl, it could be a 100 carbon chain. If we oxidize an alkyl benzene, we end up forming this molecule, which is called benzoic acid. And so any alkyl group always gets oxidized and just leaves a benzoic acid with this carboxylic acid group attached to the benzene ring. It doesn't matter how many alkyl groups or what they are. So for instance, if I had a methyl group here and maybe an ethyl group here, and I said I'm going to oxidize this. Now I'm going to oxidize this with our strong oxidizing reagents, KMnO4 or potassium dichromate. So if I react this with KMnO4 and heat, I would end up converting both of those alkyl groups into carboxylic acid groups. So all of the alkyl groups get oxidized with KMNO4 or with potassium dichromate. So that's another reaction, and we'll use this in upcoming lectures to look at the conversions of alkyl groups into carboxylic acids. It'll be a way to actually add a carboxylic acid group to a benzene ring. Okay, so in terms of this benzylic position, we're going to talk about the carbocation stability and how that can affect reactions. And we're also going to talk about right now the idea of SN2 reactions. So if you have a benzylic halide, the OH minus can come in and do an SN2 reaction on that. And the benzylic halides will react faster than other halides in SN2 reactions. And the answer is why? Well, because in the transition state to this reaction, and I'm using an iodine as a leaving group, what I will end up with is I'm going to end up with the benzene ring and the two hydrogens attached to the carbon. So here's my SN2 transition state. The oxygen will be slightly negative. The iodine will be slightly negative. As we said in the last lecture video, this carbon will be slightly positive. And so the reason that the reaction goes faster is because this benzene ring can stabilize that delta positive charge. And what that'll do is that will lower the transition state energy and lower the activation energy and make it more make the reaction occur faster, make the transition state more stable by that delocalization, by that stabilizing of the delta positive charge. So benzylic halides react a little bit faster than other halides in SN2 reactions because of the extra stabilization in the transition state of the benzene ring. Now, as far as benzylic carbocations go, benzylic carbocations are going to be stable because of the resonance structures that they can draw. You can draw with those. So let's say I did this reaction of this molecule. So I would break the carbon-chlorine bond to form that carbocation, which would have a CH2CH3 group attached to it. That benzylic carbocation is stable because of the different resonance structures that I can draw, 3 of them, by moving these pairs of electrons in the benzene ring. And I'll just go ahead and do that. If I move this pair of electrons here, I'm going to end up with the carbocation there. So what I'm doing is I have almost an allylic, I have benzylic, but it looks like an allylic, so I can now move this pair of electrons and form this carbocation, and then I can move this pair of electrons here. So there's a second resonance structure that I can draw. And then a third resonance structure I can draw by doing that. So there's 3 resonance structures that you can draw for this benzylic carbocation. And again, what I have to caution is that normally what we would do is if we were going to add the water, we would add the water to all these different carbocations, except the problem is that these 3 carbocations are not particularly stable. because I've broken up the aromatic ring. So that means that the reaction of the water is only going to occur at the benzylic position. That's where the water is going to add. And so when the water adds there, what do I end up forming? I end up forming my oxonium ion, and then the water, this pair of electrons moves to establish the zero charge on the oxygen, give it its lone pairs, but then the water comes in and catches the H plus as it leaves. So then my final product in this case would be doing a substitution on the benzylic carbon. So I would end up with this as my alcohol, and then plus H3O plus in this case. Okay, so the benzylic carbocation turns out to be a stable position, and so all of the reactions that we've done, this is going to be a stable intermediate, so that if I interpret things like Markovnikov's rule, if I could form this stable carbocation, I'm going to. And what I mean by that is that we could now say all sorts of things. We could say, oh, I'm going to take this alcohol and I'm going to react it with HCl. And if I did that, I could get the rearranged product. And what would the rearranged product look like? Well, I would take my alcohol, my OH, and I'm going to protonate with H plus. Form my oxonium ion. Then I'm going to break the carbon-oxygen bond and form water, and form this carbocation. Now, I could shift this hydrogen over and do a 1,2 hydride shift. And if I did that, I would now put the plus charge on that carbon. Remember, the rule is that you can do a carbocation rearrangement or a hydride or even a methyl shift if you end up with a more stable carbocation as a result of that. Well, in this case, I went from being secondary to being secondary benzylic. And so in this case, that rearrangement could occur. And then my Cl minus would simply come in and add there, so that my rearranged product would have the chlorine now in the benzylic position. So again, the whole idea is that this rearrangements can occur to form the more stable carbocation. And I could even go so far as to say that we could favor Markovnikov addition. So for instance, if I said here, let's go ahead and add HCl to this double bond. And you would say, okay, it turns out that they're both secondary carbons, or they're both carbons with one hydrogen. So which carbon should I add to? Well, let's write out the two different carbocations and let's compare and contrast. So if I add, let's call this carbon A and this carbon B. if I added the H to carbon B, I would end up with this benzylic carbocation, which is secondary benzylic. If I added the H plus to carbon A, I would end up with just a secondary carbocation. So in this case, the strict interpretation of Markovnikov's rule would say that we would get a 50-50 mixture of these two, except that in this case the benzylic carbocation is much more stable, right? And so being more stable, then the Cl minus would come in, add to that carbon, and we would end up with the major product, and actually maybe even the exclusive product of this reaction, to be that, versus the chlorine adding to just the secondary carbon that looks like that. And that actually, if you do this reaction, you will actually get 100% of this benzylic carbocation that forms, and you won't, you can't, this product is not detected. So you get that product of that reaction goes through the more stable carbocation intermediate. I actually know that because a student last academic year did that reaction, and we were trying to look at a situation where we could determine that the benzylic carbocation was more stable than a secondary carbocation. And so when we did this reaction, we were able to show that we got 100% of this. We didn't detect any of this product, or it was very, very small amount. I will just kind of throw out what we were trying to do, and that was this. We were actually then going to add HCl, and we did add HCl to this double bond, and our goal was to try and determine which of the carbocations was more stable, whether it was the benzylic carbocation from adding the hydrogen here, or whether it was a tertiary carbocation. And that's not necessarily well known in the literature as to which one of these two is more stable. And so when we did this reaction, it actually turned out that we got 100% of the tertiary carbocation, not the benzylic carbocation. And we're pretty confident, and that's what we got, because the chlorine added to that tertiary carbon. We're not completely sure why that's the case, but in a direct comparison of a secondary benzylic and a tertiary carbocation, the tertiary carbocation apparently is more stable if this reaction is dictated by the most stable intermediate going through the most stable intermediate of this reaction. So we're still got to figure out exactly why this is the case, but we do know that that is the reaction. So except for this case, which I'm not going to give you, normally the reactions occur so that we can get a benzylic carbocation, except this one. Now, in terms of just adding something in here, the other thing that we could think about is this. I mean, we've talked about epoxides in the past, so let's talk about epoxides with benzene rings on them. So in this case, if I said, let's go ahead and add HCl to this epoxide, where do you think the chloride will end up? On carbon A or B? And so what we'll do is we will add the H plus to the epoxide, because first step in the mechanism, always protonate the oxygen. So I'll protonate the oxygen. Right, and we're going to have that oxygen give up some of its electron density down here to the carbons. And so the Cl minus is going to add, and the oxygen really won't have much of the positive charge, so we kind of treat this as if it was a partial bond, sort of like a bromonium ion. So the chlorine now, if the total charge here is close to +1, because I added a proton to the system, where's the chlorine going to add? Well, this is basically acidic ring opening. And what we said in acidic ring opening is, where does the nucleophile go? The nucleophile adds to the carbon that is most substituted. Well, in this case, these two carbons have the same number of carbon groups attached, right? This is secondary, and this carbon right here is secondary. But the Cl minus is going to add really to the carbon that has the most delta positive charge. And so which one of those two carbons has the greatest delta positive charge? The one that's in the benzylic position. So the chlorine would add here. The OH group would swing over. So we would predict our major product of this reaction to be this product. We would expect that to be the major product. Okay. So again, the benzylic carbon is the one with the greatest delta positive charge. And when we open up an epoxide using acidic conditions, the nucleophile will add, and we should at least say this. We should modify our statement and say the nucleophile will add to the carbon with the most delta positive charge. And in this case, it would go to the benzylic carbon, because it has the greatest delta positive charge, being stabilized by the benzene ring. Now, if I reverse that, and you may say, well, what would happen if I reacted this with let's say Cl minus first, then H plus. So this is now strong nucleophile ring opening. Where's the chlorine going to add? To carbon A or B? Well, remember, the chlorine's going to add to the carbon that is least hindered. And you may say in this case, well, they both are secondary carbons, but of a methyl and a benzene ring, which one is more sterically hindered? The benzene ring. So in this case, the chlorine would come in, add to carbon B, the pair of electrons would move here. So we would then end up with the O minus on this carbon, and the Cl adding to the least hindered carbon. And then, of course, we would add our H plus step so that the alkoxide would react with the acid so that we would form Let me just clean that up. So we would end up forming that product. So we can form the two different isomers here by doing acidic and then strong nucleophile ring opening. But the key is that this benzylic carbon is the one that's going to have the greatest delta positive charge. Okay. So that's the side reactions with the benzene ring. And there are many more of them in some practice problems. And the key thing to remember is that the benzylic carbon is the special carbon, and if you can put a positive charge there, that's what you will do because it will be stabilized by the ring. Okay. Again, except for this one, which the student who did this, sometimes I just say things in class like, I wonder what would happen here. So then it's a side story. The student asked and said, well, that sounds interesting. Let's do it. And then, so we did this reaction, and when it came out completely opposite, he said, he goes, I don't believe anything you taught me in organic chemistry last year. And I began to wonder whether or not that was true or not. But for some reason, I always stumble upon these sort of reactions that don't quite fit the norm. So we can't find anywhere that anybody's looked at this. I probably shouldn't even be talking about it. But except for this one, everything normally reacts to give the plus charge at the benzylic carbon, including this one, which 100% never detect that. So again, this is kind of an anomaly. And in the past years, I just would have said, oh yeah, this is a major product. And now we know that's not the case. But I digress. So that's the special position of the benzylic carbocations. So these are the reactions that you can do on the side chains. Now what we would like to do is we would like to actually add something directly to the ring. Not the side chain, but directly attached to the ring. And before we do that, I want to add in one other side chain reaction that I've forgotten about, and that's this. What if I added Br2 in light at room temperature to this reaction? What if I want to brominate the side chain? Well, remember, this set of conditions, basically we would generate a Br dot, and we would do this by free radical halogenation, which means we're going to replace the hydrogens, one of the hydrogens, on the side chain. And so the question is, in terms of selectivity, which hydrogen is going to get removed? Well, in bromination, remember, we always ended up putting the bromine at the most stable radical position. So in this case, where would the most stable radical position be? The most stable radical would be to form the benzylic radical. So if you brominate a side chain, you're always going to brominate the benzylic position. That's even better than a that is even better than a tertiary position in terms of selectivity. Now, for those of you saying, well, wait, didn't we couldn't use this before, right, with the double bond, so we had to use NBS and heat. Okay, NBS and heat will form the same product, but in this case, I can use Br2 light at room temperature to do this reaction. Why? Because remember, the benzene ring itself, being aromatic and super stable, the benzene ring would not react, would give no reaction with bromine because it's super stable. So in this case, I can use bromine to do a traditional free radical halogenation, because the bromine won't react with any of the double bonds in the aromatic ring because they're aromatic. So you could use either one. But the critical part here is if I brominate a side chain, I'm always going to brominate at the benzylic position. Okay, so that's the extent of our side chain reactions. And then, I guess it's not the extent of it, if I took this and I said, you know what, I'm going to treat this with something like NH2 minus. Here's my NH2 minus, means I'm going to do this reaction by E2. Here's my alpha carbon. I only have one beta carbon that has hydrogens. Yes, this is a beta carbon, but it has no hydrogens. And the reason I always write the double bonds in the benzene ring is because when you write that circle, you sometimes forget that it represents a double bond. So there is no beta hydrogen here to be lost. If you put the double bond from the ring to the alpha carbon here, you would have 5 bonds, which is still not legal. So in this case, the NH2 minus would come in and remove this beta hydrogen. Pair of electrons would go here. Bromine would get kicked off in that E2 reaction, so that what you would end up forming is you would end up forming the double bond in this case. And notice that that double bond now is in conjugation with the benzene ring. So another principle that we should keep in mind is the fact that if you have a double bond that is in conjugation with the benzene ring, that double bond will be stable. And so forming a double bond then in conjugation with the ring would be the more stable double bond. So just like this more stable carbocation at the benzylic position, we'd want to keep in mind the fact that when the double bond is in conjugation with the ring, that's going to make a very stable situation. Okay, so that's all of our side chain reactions. So now let's talk about reacting on the benzene ring, not the side chain, but on the benzene ring. Well, here's the reaction that I'm going to do. I'm going to take an electrophile, an E+, and I'm going to react it with a benzene ring. But instead of doing a like 1,2 addition or doing an alkene addition, I'm going to actually substitute that electrophile for one of the hydrogens on the benzene ring. So I'm going to do a new type of reaction called electrophilic aromatic substitution. So I'm substituting one electrophile for another on an aromatic ring. And so that's what an electrophilic aromatic substitution reaction is. So what would the mechanism of this look like? Well, if this is a strong enough electrophile, what will happen is the pair of electrons in one of the double bonds of the benzene ring will be used to bond the E+. And then we'll end up with the other carbon being a carbocation. Well, now what do I have? I basically have an allylic carbocation, so that what I can do now is I can take this pair of electrons here and move it to form the double bond here and this carbocation there, then take this pair of electrons and move it to then put the double bond here and put the carbocation there. And so the resonance hybrid then of these three structures looks like this, where I have delta positive charges and then I have partial bonds in between those delta positive charges. But the issue is that the molecule has a choice to make. And the choice could be to have a nucleophile come in and add to any of these three carbocations. So that in essence you would do a 1,2, 1,4, 1,6 addition. But if you do that, then the problem is you've destroyed the aromatic superstability of the ring. So instead what happens is the molecule loses the H+, So we break this carbon-hydrogen bond, have that pair of electrons go here to reform the aromatic ring. And so we do substitution where we're substituting for the hydrogen, not addition. And that's just a very simple energy coordinate diagram. Once we form our carbocation intermediate by adding the E plus to the ring, then if we added the nucleophile to this, we would end up with a product that may have something like that energy. I'm writing really small here, sorry. But we would have destroyed the aromatic ring. I'm just going to write it above, nice and large. So we'd end up with the electrophile adding here, and then the nucleophile adding there and having the double bonds there. That would have that energy, but the more stable product would be the one where we would lose the H plus here and take this pair of electrons and give it back, so that now what we would do is we would substitute and reform our much more stable benzene ring. So we always do substitution as opposed to addition. Okay, and we'll talk a lot about these reactions in the coming lecture videos. So this is electrophilic aromatic substitution, and this is a generic mechanism for that we'll look in specific detail in the next lecture video. Only thing I need to do is I need to figure out how to make an E plus that adds to the benzene ring. So here's 3 to start with. I can add an NO2 plus to the benzene ring. So I can substitute a hydrogen and form what's called nitrobenzene. And that's done by mixing nitric and sulfuric acids together. And what happens is that when you that's the structure of the HNO3, the nitric acid. What happens is the H2SO4 basically protonates the OH group, which can then leave and have this pair of electrons go here, so that then I can form NO2 plus. And NO2 plus then will be my electrophile that will substitute for the hydrogen in the benzene ring. You could also do sulfonation and add an SO3H group to the ring. Now I'm going to write that structure out. There's my SO3H group, and this is called a benzene sulfonic acid. Now, you basically make the SO3H plus group by simply using sulfuric acid to protonate the SO3 to become SO3H. This is sometimes called fuming sulfuric acid. The reason it's fuming is because when you take the cap off of it, the SO2 gas comes out. It smokes. Now, I do want to take a little bit of a review here. So, this sulfonic acid can be converted to that species. And you might say That looks awfully familiar. If it had a methyl group here, what would it be? That would be the tosyl chloride. So this benzene sulfonic acid can be converted to a benzene sulfonyl chloride, which is that tosyl means para-toluene sulfonic acid, or para-toluene sulfonyl chloride. But in this case, what we have is we can turn this sulfonic acid into a tosyl chloride. And the reason that this is review is because if I said, what reagent can you use to convert this sulfonic acid into a sulfonyl chloride, what reagent would you say? And if you said HCl, you are wrong, because HCl doesn't work. So I need an alternative reagent that converts an OH group into a Cl. Well, let's see. In one of the last lecture videos, we talked about SOCl2. What's its job? To turn OHs into Cls. What about PCl3? Its job is to turn OHs into Cls. So either one of these reagents would be useful and would convert the sulfonic acid into a sulfonyl chloride, but HCl will not. So just those two would cause this reaction to occur. Okay, so that's review. Halogenation. So if I was to want to add a Br, substitute a Br on the benzene ring, we've already said the Br2 by itself will not react with benzene. But if you take the Br2 and you mix it with FeBr3, iron tribromide, you can form a Br plus that would actually then be able to add to the benzene ring. And here's the reason why. Because if you just have a Br, remember this is a covalent bond. And so at best, when we were doing double bond reactions, what we said was that as the bromine approached the double bond, this bromine took on some delta positive charge and eventually became a Br plus after attaching to both of those carbons. Well, since the benzene ring is going to be more stable, that's not going to work. On the other hand, if I take my Br2 and I react it with FeBr3, then what will happen is the bromine bond will break and the pair of electrons from a Br minus will go to the iron. So what I'll end up doing is forming a Br plus by itself and then FeBr4 minus overall because it picked up a Br minus. So it's a difference between trying to make a little wimpy delta plus charge here and delta minus where it's polarized but not a full-blown charge, whereas when you use FeBr3 as essentially a catalyst, it will form a full-blown Br plus, which is now a strong enough electrophile to add to the benzene ring. So you can do this with Br2 and FeBr3. You could do this with Cl2 and FeCl3. You can also do it with the aluminum trichloride reagents as well. So that means that I can make a Br plus, or I can make an SO3H plus, or I can make an NO2 plus, and each one of those electrophiles would add to the benzene ring like this mechanism, so that I would do substitution and form either a nitrobenzene, a benzene sulfonic acid, or to form something like bromobenzene. Okay, so those are the first three ways that we can form electrophiles. We're going to have a lot more reactions to learn about, but we'll leave the introduction to this here. And in the next lecture video, we'll go ahead and talk about more reactions to form electrophiles and get into the much more complicated situation of, if I wanted to add a nitro group, what if there was already a benzene or a group on the benzene ring? Would the nitro group, so for instance, if I wasn't to react benzene because benzene's boring, what if I was to have a methyl group here? Where would my NO2 plus end up substituting? Would it end up substituting at the ortho position, or the meta position, or at the para position? And so that's why we learn those terms, ortho, meta, para, because we're now going to use them. Okay? So that's our reaction. That's our initial electrophilic aromatic substitutions, and we'll talk more about these in the next lecture video.